Okay, so I started grading the exams this morning. I have no idea how long it's going to take me to get through all sections. I'm hoping to get a lot done today. Once I have them all graded, occasionally, and I like to say this kind of going into the exam, occasionally I'll do kind of a small curve on it, depending on where the average is at, and if it's kind of around where I want it to be, usually somewhere between like a 75 and an 80. So usually not quite as high as 80, but I'm kind of hoping, kind of based off of if I look at the multiple choice, kind of the average is there. I'm thinking the average should be right around there, but if it's a little low, I may add kind of a small curve. If I do that, I'll post an announcement about it. Also, once I have all of them graded, I'll be replacing kind of the old exam with what looks like a new one, but it's basically just your score, and then it's taken out of 100 instead of right now it looks like it's out of 104 because of that bonus question. So if you kind of see a second exam pop up, I'll probably call the original one like raw scores, and the second one just exam one, where it's just grading you out of 100. Okay. So, like I said, I'm hoping by next class I'll have most of those I'll have all the exams graded by the time we start class Wednesday, and have a little bit more to say about kind of where the average was at and things like that. Any questions for me? Kind of moving forward? Probably not, since we just had an exam. But we're going to start on kind of the next topic. It's going to be using some of the stuff we've already talked about, right? But kind of a different, okay, I'm making sure I was recording there, right? I got freaked out. So it's going to be like what we're doing with discrete random variables, except for now we're going to be dealing with, start from here, continuous random variables, okay? So things are becoming a little bit more difficult. We'll talk about two types of continuous distributions specifically and some of the properties that they have. But a lot of the things we've been using will kind of apply to these random variables as well. Okay? So, we've kind of had this before, just kind of a quick review. When we're dealing with a continuous variable, it can be the integer values, but it can also be anything in between, right? 6.3194. Okay? So there's essentially no gaps in the responses that we could see for this variable. It's still going to be, we're dealing with random variables, so it's something that we don't know what the outcome is going to be, and we know there's all these different outcomes that it could be, and they're all going to have kind of the different probabilities associated with seeing them. Right? The values kind of around the mean will be more likely, the values further from the mean less likely. So, we talked about kind of income, we could look at interest rates, whatever variable we could see any decimal answer for, okay? Or any outcome, or the outcome could be any decimal value. So just like with discrete random variables, we're going to have a probability density function or probability mass function for these continuous distributions as well. Right? Now, one thing that's kind of unique, and as we work through this, I'll kind of point out a couple times why this is the case, but we can only find the probability over certain intervals. Okay? So the easiest way to think about this, I'll go back there in a second. So we can only find the probability over certain intervals. So if we switch over here, let the system catch up with us here. Maybe, there we go. Oh, there we go. We're flashing it on and off in class. So, when I'm thinking about kind of the most simplistic kind of drawing of it is kind of thinking about these continuous distributions where there's some variable x, and we could see it take on any of these outcomes, right? So if we think about what's on the y-axis here, it's kind of like the probability associated with each one of these outcomes. If you want to think about it as discrete, just to kind of help us move from discrete to continuous, you can almost think about it as at every single x value, there's like these really, really small rectangles that would give us the probability, and they're kind of building out this distribution for us, right? But now instead of kind of drawing them as these bar graphs, because it's truly continuous, we can kind of get this nice continuous line where the probability of each one of these outcomes x is kind of represented by that point in the line, right? You can go over the y-axis and find that probability. Now, what we're going to unfortunately have to do is instead of looking for the probability of any one value, we're going to have to start to look for the probability over a certain range, right? A certain interval. So maybe that's from 5 to 10, or maybe that's the probability I see it go from what? I don't know, not 10, 20 to 21. And we're going to be starting to think about probabilities over a certain space, right? Now, when it was discrete, we were doing that, right? We could still find the probability it was between 2 and 4. It's just that we knew what outcomes were in between 2 and 4, right? We only had a couple. Now, what are the number of possible outcomes between 20 and 21? If it's truly continuous, how many numbers are there between any two numbers? If it's truly, you could see it out to any decimal you wanted. Infinite, right? We can't count that high, right? So it starts to present us some problems, because let's think about the most simplistic type of continuous distribution, where everything here, some numbers are more likely than others. Let's think about one where every outcome is equally as likely. So let's say we only had 100 outcomes, right? If it was discrete, and every outcome was equally as likely, what would be the probability of any one outcome? They're all equally as likely. We've got 100 different outcomes. Each one would have a probability of? Wouldn't have a probability of 1, right? If we think about there's 100 different possible outcomes, if we added up the probabilities of those outcomes, it would add up to 1. But each outcome would have a probability of 0.01, or what did you do there? You really took 1 over 100, or didn't matter if it was 100 or 500 or 10,000. Everything would be 1 over n as likely, right? If we only had 4 outcomes, the probability of each outcome is 1/4. Right? If we have 10 outcomes, the probability of every outcome would be 1/10. Well, what happens when you have an infinite number of possible outcomes? 1 over n, well, your n becomes infinity, and basically, in the limit, we say this approaches 0. Right? So the probability of any one outcome is essentially 0. Well, this is a problem, right? It's not intuitive. It kind of messes with our mind in the sense that the probability we see exactly 5, if it's a truly continuous variable, the probability we see exactly 5 is 0. But the probability we see between 5 and 10, or 5 and 6, or 5 and 5.1, we can actually get a probability for that. I know that that's a kind of a hard concept to grasp, but really, if we truly have an infinite number of possible values, the probability of any one outcome is 0, but the probability of any interval is actually not, has to be positive, right? Something above 0. Now, it might be very, very close to 0, but it's going to be something above 0. So this is kind of where we're starting. It's kind of a weird thing compared to the discrete random variables, but this will we'll kind of see this idea that the probability of any one outcome is 0. That kind of pops up as we kind of start to move through these continuous random variables. Okay, and I'll kind of touch back on that a couple different times, not just today, but probably next couple classes. So if we wanted to use describe this with a table or graph, see if I can get this up on the screen out here. Tick, 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 tick. Come on. Wait for the screen in class. There we go. Right, I drew that kind of line that displayed the distribution, and that's going to be my probability density function, right? It's going to be some function that's going to allow me to find the probability over certain intervals, right? Now, I'm not going to expect you to do the calculus, but if I had the actual function that gave me this line, I could integrate, from 5 to 10, find the area under this function. What that's really telling me is that's the probability of being between 5 and 10, right? Once again, if you think about this as a bunch of really small rectangles, it would essentially be adding up all those rectangles, right? Now, that's kind of just a way to conceptually think about this. Obviously, it's these would be infinitesimally small rectangles, but that's the general idea. It's kind of like how they try to teach you calculus. They usually kind of take an approach like this, right? So we want the area under that curve, but between these two values, that's really kind of integrating from 5 to 10 from that, using that function that would give us this line. But I'm not going to make you do the calculus, right? We have ways of getting around this, so we'll kind of touch on those as we start to deal with some kind of nastier looking functions like that. But whatever the function is, right, whatever that probability density function is, we know that the probability over any interval, right, has to be 0 or positive, right? And at most it could be, if I can get this on here, at most, right, if I went across the entire interval, right, from the very lowest possible to the very highest possible number, and I integrate that function, essentially what I'm doing is I'm finding the kind of area. If I integrate it across every possible value for this function, I'm integrating that area under the curve of my distribution. Well, that's essentially taking the probability on each one of these small rectangles. It's adding up the probability of every single possible outcome. And if we add up the probability of every possible outcome, the same principle applies as when we were talking about discrete random variables or relative frequencies. Those would have to add up to 1, right? Because this function is, translating these different values for x, these different outcomes, into probabilities. So essentially, I'm adding up the probabilities of every possible outcome. That would give me the area under the curve. So the area under that curve has to be 1. The area under that curve, we can almost think about, it was easier when we had simple examples where we could think about it with like a Venn diagram. Essentially, the area under the curve is that rectangle. It's in the entire experimental outcome space, which is equal to 1. Any questions? We also kind of don't see any sudden jumps, so we're going to have this kind of nice smooth line. We're never going to have it where it goes, I don't know. So we had a different functional form where it did something like, we'll never see kind of a jump, right? It's going to be this kind of nice continuous line. Okay? Now, we won't be looking at any goofy shapes like that, but that's kind of what that condition is referencing. So integrating that function over every possible value we can see for x is essentially the same as adding up the probabilities of every possible outcome, which gives us that 1. So I've already been drawing this, but we can draw out these distributions. We can just use that function, plug in the different values for x, get the point at which, what y value that x would translate to, which kind of is the density, right? That probably density function, what that's going to return to us. We could graph out that entire line. Right? So it's kind of nice. Now, we think about visually the area under this curve that represents our entire experimental outcome space, or that area should be equal to 1. Okay. Any questions on this up to this point? All right. So we can also come up with a cumulative density function, right? And with the cumulative density function, we'll just call this capital F of x instead of lowercase f of x. Capital F of x is going to tell us not the probability of seeing that one value for x, but the probability we see that value or anything below it, right? Just like cumulative GPA, the probability, your GPA in this semester and every semester below it. So cumulative density function, the probability we see this x value or any outcome below that. So, as we kind of get to those higher x values, that cumulative density function, similar to when we've talked about cumulative density functions in the past, it'll approach 1. And when we look at really, really small values of x, that cumulative density function will be really close to 0. Okay. So if we want to think about visually what this is going to look like for our area under the curve, let's say I have that cumulative density function, and for the value of x, I plug in some value a, right? So I kind of thinking about whatever a translates. Could be 10, could be 100, whatever x value I'm interested in. If I plug that value of a, whatever that number is, into my cumulative density function, my cumulative density function will tell me the probability I see that value of a, right? That x is equal to a or anything less than that. So what I'm really thinking about is the probability I see a or any value below it. Well, like I said, if you could draw infinitesimally small rectangles for each one of those x values and then add them all up, you're really just looking for the area under that curve. Okay? So that cumulative density function is essentially going to tell you the area under the curve from the very smallest x value you could see all the way up to whatever value a you're interested in. Okay? So we can kind of think about, we can shorthand this. The probability that x is less than or equal to a is just what I would get if I plugged a into that cumulative density function, capital F of a. Okay? So let's start to kind of play around this a little bit then. So what if I wanted the probability that x is greater than b? How could I how would I write this out using that cumulative density function? How could I find the probability I see b or any x value greater than that? Well, I know the cumulative density function. If I plug b into that, right? So if I want the probability that x is less than or equal to b, right? You can kind of write that as, well, I'll just use my cumulative density function, right? That would give me the probability I see b or anything below it. I know this kind of looks like a 6, but maybe I should write a capital B here just to kind of be clear. So if this gives me the probability I see B or anything below it, how could I get the probability I see B or anything above it? Well, this is where, yeah, so it's going to be a little bit interesting. So think about here, if this was my event, and we'll call this event A, then that's the same thing as 1 minus the complement, which would be that X is greater than B. Now, here you might say, well, you wanted the probability X is greater than or equal to, so we had a problem here, right? This is where kind of that initial thing that the probability of any one event is equal to 0, it gets a little weird, but I'll kind of show you the intuition here. Right? So you could think about this as, oh, sorry, I wrote this out for something else. Let's do this again. So I was using this to kind of to explain to you, and then what the actual slide had was what, let me see. Right, the actual slide was saying what? We wanted the probability X is greater than or equal to B, right? So if this was event A, that should be equal to 1 minus the complement, which here if A is that X is greater than or equal to B, the complement would be that X is less than B. Okay? Well, what we set up here, if we plug B into the cumulative density function, that gives us the probability X is less than or equal to B, right? But that's okay, because the probability of any one value is equal to 0. So this is where it gets a little weird, but I could actually add to this the probability that X is equal to B, and if the probability of any one value is equal to 0, I actually didn't change this equation. It's really weird to think about. You just kind of gets into kind of like some real analysis, kind of math stuff, but essentially if the probability of any one value is 0, I haven't changed this equation at all. And what this is really saying is just what's the probability that X is equal to B or anything below it, right? So that actually, I could rewrite it like that. So now to get the probability X is greater than or equal to B, it's just 1 minus the probability it's less than or equal to B, which I could use that cumulative density function to find, right? Or another way to think about this visually, I can put that back up in just a second, is if this is truly continuous, and I have the value of B here, if the area under the curve is 1, and the cumulative density function for B would tell me the probability I see B or anything below it, well then how could I find this area? Well, if the area under the curve is 1, I know these two things have to add up to 1, so it would just be, right, 1 minus that cumulative density function. So that's kind of what's going on behind the scenes, and we're not going to like, I'm setting some of this up for once we get to the continuous random variable that is the normal distribution. We'll kind of be doing this without thinking about it, but this is going to be going on in the background of what we're doing a lot. And this was kind of the mathematical reasoning behind that. All right. So I'll leave this up for a second here. Wait for any questions, see if we have any questions over that. Okay with that? Okay. So, you know, if we think about the probability that X is greater than or equal to B, it's the area under the curve, but above B. And we said we could have found that by taking 1 minus the probability of being less than that value. So what if I want the probability, I'm in between A and B? Well, if I use that cumulative density function and I plug in A, that will give me the probability I'm under the curve, but less than or equal to A. Oops, sorry. I think I had my things out of order. Wait. Oh, okay, never mind. I'll do this off the slides. I thought I had some in overlays, but I don't. So if we want the probability of being in between A and B, what we're really thinking about is I'm in between A and B, the area under the curve. I could add up all those probabilities. So the area under the curve between A and B, that gives me the probability I'm in between A and B. So, kind of give you some intuition behind that one, right? So let's say I wanted to think about being in between A and B here. Right? If I use that cumulative density function, it gives me the probability of being less than or equal to that value. So I could use the cumulative density function to find this area, right? I could then use the cumulative density function to find this area, right? By just plugging in B there. So if all I wanted was the probability I'm in between those two, if I have the entire, and I drew a circle around this, you could think about almost like shading the area under the curve all the way to the left in red, and then shading the area under the curve in black all the way to the left of A. If I just subtract out this tail from this larger tail, what I'll be left with is just what's in between those two values. So I can use the cumulative density function to find f of B, right? Kind of gives me the area to the left of B. And then I subtract the area to the left of A, and that would leave me just what's in between the two. Okay? So that's where that came from on the slide, where I can take the cumulative density function for the larger value, subtract the cumulative density function for the lower value, and that would give me the probability that I'm just in between those two. All right. So that's where we're at here. You know, this isn't anything crazy, but what if I wanted the probability that I'm less than or equal to A, but greater than or equal to B? Well, if I had the area in between the two, I could just subtract it from 1, right? So what gave me the area in between the two? That was this, right? So get down here. Oh, right? If I just kind of took that light gray shaded area, subtracted it from 1, it would give me this kind of brighter kind of blue area in the tails, right? So really at this point, it's almost like if you draw the visual out, it becomes a little bit easier. You're kind of just piecing different, you're taking different pieces under this curve and then kind of thinking about, okay, well, if I had this light gray area, the area under the curve is 1. I know then to get the tails, I could just subtract that light gray area from 1. And like I said, well, a lot of this we'll be doing kind of comes a little bit behind the scenes that we don't think about that we're doing it moving forward, but this is kind of the fundamentals. No matter which distribution, the normal distribution or whatever distribution we're looking at, we could use these same principles. Okay. So the rest of today, what we're going to do is talk about not the normal distribution, but we're going to start out talking about an easier distribution, which is the uniform. Okay? So the uniform distribution is this idea that every equally sized interval is equally as likely. Okay? So if I want the probability that I see the outcome be between 1 and 2, that's the same as the probability I see it between 3 and 4. Or the probability I see it between 10 and 10.1 is the same as the probability I see it between 15 and 15.1. Equally sized intervals will have the same probability of occurring. Okay? So my density function is going to end up being 1 over, and we kind of use D and C here. Almost if you want to replace them, this is really just 1 over the range, or the maximum, which is D, minus the minimum, which will be kind of C. That kind of tells us where this uniform distribution stops and starts. So if I'm thinking about a uniform distribution, everything's equally as likely. So I'll kind of use ranges of 1 to make this a little bit easier to think about. So let's say we have this uniform distribution, all the different values we could see. Right? So let's think about if what I'm telling you is true, right, that the probability kind of density function is 1 over the range, right? We could think about we have some minimum here, which we're going to use and call C, and then some maximum here, which we'll call D. Right? So what is kind of the height of my distribution, right? Well, if everything's equally as likely, then let's say the minimum is, I don't know, 0. Okay? So what's the probability I see an outcome between 0 and 1? Well, it's going to have some probability associated with it, and whatever that is, we could kind of plot that point on our y-axis, right? I don't know. Let's say the probability between 0 and 1 is 0.1, right? So we're plotting this on the y-axis here. Well, then what would be the probability that I'm in between 1 and 2? Well, if every equally sized interval, right, this is intervals of size 1, if they're all equally as likely, it would have that same probability of occurring, right, 0.1. And then what about the interval from 2 to 3? Same probability of occurring. We would kind of continue to do this all the way till we get to our maximum. Let's assume our maximum is 10 here, right? Then we'd have what, 10 intervals, all equally sized, right? 10 intervals of size 1. So each one of those intervals should have a probability of 0.1 of occurring, right? They're all equally as likely, right? So if you break down your range into kind of like integer values, right? It's not that this is discrete. We could still see 0.5, but the probability we see something between 0 and 1, well, that would give us kind of 10 equally sized intervals, all the same probability, so each interval would have a probability of 0.1. So what we're going to end up with a uniform distribution is kind of this rectangle, right? Here's our minimum, here's our maximum, and then everything's equally as likely, so that y point, right, the y-axis point, our y-axis is still kind of giving us this, this probability mass or probability density function. It's giving us a probability, so we're just going to end up with a flat line, right? Everything's equally as likely. Now, if I want to think about, okay, this ends up being 0.1, but why did I ahead of time know that it was going to be 0.1? Well, first of all, I knew I was going to choose 0 and 10 as the min and the maximum, right? But that probability density function told us that the height of this distribution will be 1 over d minus c, which I said that really is just saying 1 over the maximum minus the minimum, or 1 over 10. And then so any interval of size 1, right, there would be a probability of 1 over 10 of occurring, or 1 over that range. I'll go a little bit more into detail in the next example of this, but this is kind of where that comes from. And then here when this says 0 otherwise, all this means is that technically, if we want to be real technically correct, anything outside the range of 0 and 10, right, the minimum and the maximum, the probability is 0. So technically we have like, our uniform distribution is a rectangle with kind of like legs going along the x-axis at 0 on either side, right? That's all that 0 otherwise means. All right, so we already talked about those. So if I wanted the probability I'm in between any two values, A and B, this is going to end up giving me a cumulative density function, or not even cumulative necessarily, because it's not cumulative, sorry. It gives me the probability I'm in between those two values. This function would do that. So why does that work, right? So if we want the probability of being in between any two values, it's going to be wherever that interval starts and stops, right? The kind of length of that interval divided by my range, my maximum minus my minimum. Okay? So where does this come from? I'll wait to kind of switch over to just the docking here. I can see people are still writing in class, okay? All right. So where this comes from, let's use this same kind of setup, right? Where I'm going from 0 to 10. Because I think it's easy to think about. So we've got 10 is my maximum, 0 is my minimum. All right, we can think about this as C and D, right? So we said that the height, right, was 1 over 10. That came from the fact that we were looking at 1 over D minus C. So this 1/10 really was representing to us 1 over D minus C, okay? If I then wanted the probability, let's say that I'm in between 4.5, I don't know, let's do 6.5. Okay? So what I really want is the area under the curve. Now my curve here is a flat line, but it's still the area under the curve, but in between those two values. So this is kind of where my interval starts. This is where my interval stops. This is just the area that I want, is the area of a rectangle, right? This is a rectangle. I want the area of a rectangle. All I do is, and I haven't done geometry long, I think this is probably base times height, or I don't think they call it base, right? Like length times width, right? All we're going to do is take the length, or I guess the width of that rectangle, multiply it by the length, or multiply it by the height, right? Whatever you want to call it. The two sides of the rectangle right? Find each one and multiply them by each other. So what is the kind of width of my rectangle here? Well, if I look at that, it's 6 minus 4.5. Well, all I'm really saying there was it's b minus a. Right? Doesn't matter what a and what b are. Doesn't matter if they were these values. We would still just take the high end of the interval, subtract the low end. So that's kind of like my width. What's the height of this triangle? What's the length of this triangle? Well, it goes from 0 all the way up to 1 over 10 or 1 over d minus c. Right? So kind of think about here, my height is 1/10 or 1 over d minus c. So if I then want the area of that rectangle, I'm just multiplying that width by the height. So b minus a times 1 over d minus c, which if I simplify this a little bit, I could rewrite as that. And in my scenario, it would be what? 2 divided by 10 or 2/10. I'm just plugging in my values there. And that kind of makes sense because if I have a interval of 10, right, those are the only possible outcomes I could see are between 0 and 10, but every outcome is equally as likely, well then the probability I see something in an interval that is of size 2, well it's of size 2 out of the entire interval of 10, so the probability I see something in that interval should be 2/10, which is, sure enough, what it ends up being. Now, I chose some pretty nice, easy numbers for this example. It becomes a little more difficult when we're going from things like, I don't know, negative 39.2 to 174.135, right? It'll become a little bit more complicated, but it'd be the same idea, right? I'm just really looking for a small rectangle, and what proportion of the entire rectangle is it? Because what's the area of this entire rectangle? The area under the curve should just be 1. This is my curve. It starts and stops here. So the entire area under my curve, or this entire rectangle, should be 1. Sure enough, if I wanted to try to figure that out, what would if I wanted the probability of seeing anything in this rectangle, what's the height? 1/10. What would the width be? 10 minus 0 or 10. 10 times 1/10 or 10 over 10 here would be a probability of 1. And so that kind of, I don't know, confirms or gives us kind of confirmation this uniform distribution is following those properties of our continuous random variable, such that the area under that curve, right, is equal to 1. Excuse me. Any questions on that? We keep moving. All right. Let's make sure we get switched. Okay, awesome. I think it's always just the first time that it doesn't switch over for us here in class. So, I've kind of already given you these visuals, but right, anytime you have the minimum and maximum uniform, you can automatically draw what that distribution is going to look like. We know the height will always be 1 over that range, right? In our example, this is 1/10, right? So what are going to be some statistics we can calculate from this uniform distribution? I was grading too many binomial stuff earlier. I was thinking about it still. Well, the expected value, if I go to even an example like the one I had here, right? If it goes from 0 to 10 and everything's equally as likely, well, where's the middle of those outcomes going to be? What's just kind of the average of your minimum and maximum, right? So you add up your minimum and maximum, divide by 2 or find the average of the two, and that's going to give you your mean, right? When we calculated the mean, I think at one point I even kind of wrote out the mathematics that everything really we could think of as being weighted by the same amount, right? When we found a mean, it was actually kind of like finding a weighted mean, where everything was just weighted by 1 over the number of observations, right? So same kind of idea here, right? If I can see anything from 0 to 10, right? I'm looking for the mean. It's just going to be kind of what that middle value is, because everything's going to be weighted equally on either side. So I just have to kind of find a normal mean where that's going to just be what's exactly in the middle. Now, nice thing about the uniform distribution, the mean here would be what? 5? Well, that's also going to be the median, right? 50% of the outcomes are on either side. So we have a nice symmetric distribution when it comes to the uniform. Right? If we look at the mean, it'll always be equal to the median. I kind of split that distribution exactly in half. Now, if we want the variance, it's not going to be as intuitive. It's kind of like the binomial, right? The mean was intuitive, but the variance wasn't, right? We just have an equation we know works, right? We could go through the mathematical proof, right? We now have a formula for our mean. We have that probability density function for every single possible outcome X. We worked a little bit of math and some, did some simplification. It actually doesn't matter what your minimum and maximum are. Your variance always simplifies to this, which is simply the range squared divided by 12. Okay? Or maximum minus the minimum, square that difference, divide by 12. Like I said, this is really just kind of writing out that probability density function, subtracting the mean, squaring it from every possible value of X. We can always simplify it down to this. And if we want the standard deviation, what's the only other thing we should have to do? Just take the square root, right? That's always, always the same thing. So, we've got our equations now. It doesn't matter what example we had. We could always find the mean. We could always find the variance using these two formulas for a uniform distribution. So if we had kind of an example here. So I pulled some old cheesy Hulk Hogan movie I recalled from my childhood. But let's say they're going to come out with Mr. Nanny 2, right, based off how successful the first one was. Now we're not going from 0 to 10. Let's assume that the demand for popcorn is uniform, right, at this, whatever theater this is, and it goes from 1 to 10 pounds. Right? So we've got our minimum, right, the way we write the uniform distribution is we've got this variable X, or demand, which is uniform and distributed, and it starts at 1, stops at 10, right? So we've got a minimum of 1 or a maximum of 10. What's the mean popcorn demanded? Well, if you think about kind of working this one out, go back here. Got a slightly different example now where my demand for this variable starts at 1, ends at 10, but I know it's uniformly distributed. Okay? So when I'm looking for the mean, I'm looking for the value that's smack dab in the middle of my minimum and my maximum. Or another way to think about it is I'm just finding the average of these two. Or if I wrote this out mathematically, add my maximum and minimum together and divide by 2. So 10 plus 1 over 2 would give me what? 5.5. So here's something I want to point out that I haven't mentioned yet. But what's the probability that I'm less than 5.5? Remember, I said this is a symmetric distribution, so the mean is equal to the median. So what's the probability I see something to the left of the mean? Yeah, if it exactly splits this in half, well, I know the area under that curve, or under my straight line here for this distribution, is 1. So if it exactly splits that area of 1 in half, I have 0.5 on either side. Right? So that's just kind of a principle we can think about. We're looking at these symmetric distributions, which is the uniform, and we'll end up seeing is also the normal. The area to the left and right of the mean is always 0.5. Okay? So we already answered kind of where the mean's at, 5.5, right? And this is just kind of a reminder. If I'm thinking about, if I want the area, or probably I'm in between two values, I can find the width of that rectangle and then multiply it by the height, which I know the height is always 1 over the range. So here, my height is going to be what? Well, if we think about, here's my maximum D, here's my minimum C. The height is just 1 over 10 minus 1, or 1/9. So if I go into the next problem with that knowledge, it should become relatively easy. So let's say, what's the problem? We've got this same sort of movie, and it's had the great cheesy graphics. I pulled this clip from it. So if the movie theater makes 9.5 pounds of popcorn, what's the probability they didn't make enough and they're going to have angry customers, right? Or essentially, what's the probability that I see demand be equal to or greater than 9.5? Right? That's what I'm looking for here. What's the probability demand is 9.5 or higher? Well, if I think about this, if I draw this out visually, what I really want is the probability that I see demand be 9.5 up to 10, right? Because I can't see anything past 10. That's the maximum amount that this variable is set at. Well, right away, what does this probability have to be less than? If I look at the mean of 5.5, the probability I see something above 5.5 is 0.5. So I'm looking for a much smaller area than right. If the probability of seeing something demand be 5.5 pounds or higher is 0.5, well, then the probability it's above 9.5 has to be something smaller than that, right? This is an area smaller than 0.5. Right? That's all I can really say at that point. So, if I'm thinking about, we go back here, right? C doesn't make any sense for us, right? We know the probability, if we express it as a percent here, has to be less than 0.5. Okay? From that simple kind of principle that the mean is equal to the median and exactly splits this distribution in half. But from there, what's the width of my rectangle? Well, it goes from 10 to 9.5. I could then multiply that by the height, which we had up here was 1 over 9, or 1 over 10 minus 1. Well, that's going to be 0.5 times 1/9. I think that's going to be 1/18, so 0.056 maybe. Let's see. Yeah, if we worked it out, it's going to be 0.056. Just having some trouble doing that math in my head there. Now, the other way I could have done this was, the more kind of general formula that we have is B minus A over D minus C. If I just would have plugged everything in, my interval stopped at 10, started at 9.5. My maximum was 10, my minimum was 1. This will give me the same thing, right? I just always think it's easier for me. I don't know, maybe it's just the way I think. But when I draw this out and I can visually see I'm just finding the area of a rectangle, and I've already plotted the height, and I can kind of look at the width pretty easily there too, that just always makes a lot more sense for me. It's up to you. You can always use the more general form of the equation and plug those values in, but I always find it kind of easier to do it that way. Okay. Any questions over any of this? Okay with that? All right. So we got what, 0.056 there? All right, if we plug everything in, or kind of the method I showed you of thinking about it as the area of a rectangle. So what's the probability that they make 9.5 pounds of popcorn and they make exactly the perfect amount, right? That demand ends up being exactly 9.5. So what should the probability that they make exactly 9.5 be? Yeah, someone's holding up their hand, right? Because I already said this earlier. The probability of any one value that is exactly equal to one value should be 0, right? But we can prove this to ourselves, okay? So let's say I have this same kind of setup. Well, I could probably draw it in the same graph, right? Because we have the same height of 1/9. Let's say, what's the probability I see exactly, I said it was 9.5 in the problem, but just so I can kind of draw things, multiple things here on the same graph. What would be the probability I see exactly 8.5? Well, where would my interval start and stop here? If it's exactly one value, my interval actually starts and stops at the same thing. So now if I plug in B and A, it's going to be 8.5 minus 8.5. So whenever I'm looking for the probability of any one value, that numerator would always be 0, or the width of my rectangle is always 0. Well, 0 times anything is 0, right? So that is one of the principles of any continuous random variable, but we can see here, even if I had worked it out and thought of my interval as being this, I say infinitesimally small, but essentially non-existent, right? It starts and stops at the same point. We would actually work it out and we'd still find that the probability is equal to 0, right? Even if we didn't remember that kind of principle. So this kind of backs us up. I'm not completely full of it, right? Or at least so far in the context of this distribution, okay? All right. So go back here. It's kind of, I use 9.5 here because I used 8.5 just so I could show you a little bit easier, but essentially we're always going to get 0 there if we're looking for the probability of any one value. Where are we at in time? 5 minutes. So this is not in the slides, but I want to go over something else here. So what if, let's say I've got this, and just as a reminder, the probability I was between 10 and 9.5 was 0.056. Okay? So what if I wanted to find the probability I was in between 2.5 and 3? With very little work, you should be able to tell me what that probability would be. 0.056, the exact same. Why? Well, this interval was of size 0.5. This interval will be of size 0.5. Or you can think about it differently. We've got rectangles with the same width and the same height, right? So any equally sized interval, even if we plug the numbers in, ends up working out so that it has the exact same probability of occurring. What if I wanted the probability that I was in between 2.5 and, let's change this instead, we'll say 3.5. Well, now, if an interval of size 0.5 has a probability of 0.056, what would an interval of size 1 have? It's twice as large, so I would just, multiply this by 2. You get what? 0.112 if I'm doing this in my head. Okay. So once you kind of find one interval, like as long as it's like somewhat of a nice clean number, if I asked you to find an interval that was like 0.315792 and it didn't, wasn't divisible into many other numbers. But if I give you something simple like this, we can start to find probably different intervals pretty quickly. We don't even have to plug all the numbers back in, just kind of remembering that concept that any equally sized interval has the same probability of occurring. Okay. Any questions on that? Or what if I said, what's the probability I saw less than 9.5 pounds of popcorn be demanded? Well, if I know the probability that more than 9.5 is 0.056, how would I find the probability, that I'm less than or equal to that 9.5? If I know this black shaded area is 0.056, what would the, if I did shade all this blue, what would that area have to be? Yeah, right? Area under the curve is 1, subtract out that 0.056, right? So, you can start to think about, adding in some of those things we talked about earlier to this uniform distribution once we get kind of comfortable finding these probabilities of any one interval. Any questions on that before we keep going here? All right, so that should wrap us up for the day. Like I said, I don't have, I should have those exams graded. I'm hoping by the time we start class Wednesday. Might be a little bit close, but I'm thinking I should have them and be able to talk a little bit more about them on Wednesday. I'll put up an online quiz for today that kind of has some easy questions about a couple things that we talked about in class. That'll be due before Wednesday's class starts. Other than that, we shouldn't have any kind of outstanding homeworks or anything right now, so you don't have a whole lot to worry about. I said that, but I am going to put up a Learn Smart. It's about a chapter that's a little bit further away, so I'll look at the dates and I'll probably set it so that you read it by next Monday. I don't think we'll get to that material before then. Maybe touch on it a little bit Friday. So I'll set that so it's not due until Monday, but it should be 10 minutes, pretty quick. Go through it, get the full points. Okay. All right. We'll see you guys on